Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad, EC Department. So today in this video lecture, we will understand how to design a synchronous counter. The synchronous counter is the counter in which we are giving clocks simultaneously to all the flip-flops. So we can design synchronous counter using JK flip-flop, T flip-flop and D flip-flop. But we need to understand, before going to the designing of the synchronous counter, we need to understand the excitation table of all the flip-flops. So we have already understood the characteristic table, how to write the characteristic table for the flip-flops. Now we will understand how to write the excitation table for all the types of flip-flops. So we are having 4 types of flip-flop: SR, JK, D and T. Now we will understand the excitation table and then we will move to the designing of the synchronous counter. So here coming to the SR flip-flop. So as we know, the SR flip-flop, when we give input 0 to this S, the next state is always 0. So here for 0, 0, there will be no change. If Qn is 0, then Qn plus 1 will be 0. And for 0, 1, also the Qn plus 1 will come out to be 0 or reset state. So this is the representation for no change condition and for the reset condition. So for 0, 0, if the present state is 0 and the next state is 0, so there are 2 possibilities. First is for no change and second one is for reset. So we have put the cross for 0, 1 and for 0, 0. So it will be 0 cross. Similarly, for the case of Qn 0 and the next state is Qn plus 1. So for Qn plus 1, if the present state is 0 and the next state is 1 and the input S is 1, just because of the condition is for set. Whenever you give the set, since 1, 1 is not defined for our SR, so we cannot take here 1 cross. Only we will write 1, 0 for 0 to 1. Right. Similarly, next state for Qn is 1 and Qn plus 1 is 0. So Qn plus 1 is 0 if we give S to be 0. Okay. If S to be 0, and what should be the condition for 1? Let us find out. So the earlier output was 0, earlier output was 1 and the next state output is 0. So we can say this is the condition for S and R to be 0 and 1. So 0 and cross we have already mentioned. 1 and cross, 1, 1 is not possible, so we cannot make it cross. So this is the condition that our flip-flop is getting reset. Now for 1, 1, there is a cross R. 1 to 1, that means whether it is a no change condition or this is a set condition. So hence the characteristic table for SR flip-flop can be written. Similarly, for the D flip-flop, the Qn plus 1 is always equal to the D. So we can easily write the excitation table for the D flip-flop for Qn plus 1, all the 4 combinations. Similarly, here for the JK flip-flop, if we see, since here, as in this case, 1, 1 input is not defined, but here the 1, 1 input is defined. So we have all the conditions for this and the characteristic, like for 0 cross, the 0, 0 may be condition, that is for no change and the reset, 2 possibilities, and 0 to 1 for 0 to be 1, first is set and another one is 1, 1, the toggle. Okay. And for cross 1, that means if the Qn plus 1 is 0, sorry, this is set. This is set obviously. For 1 and 0, see here, these are two conditions. For is if qn plus 1 is 0, so it will be reset and maybe toggle. And here 1 1, that is no change or set, right? So here only one condition was there. Here toggle has been added because in JK flip flop we have one more condition, that is toggle. Similarly here for the as far as this excitation table for the T flip flop is concerned, wherever the outputs are same, qn and qn plus 1 are same, T must be 0. And here the toggle conditions and the toggle conditions. So the for toggle T must be 1. So we can write the characteristic table for the same. Now these excitation tables for all the flip flops we can use for so many purposes. Let's say for designing of finite state machines, Mealy Murray, maybe designing of the counter. Also for any sequential circuit design we can use these excitation table for flip flop conversion, as we will see it in the next lecture. So here let us suppose we have an example that we need to design a synchronous 3-bit up counter, and we are given that we need to design using the JK flip flop. So since there are 3 bits up counter, so first of all we will make the state model. Okay, so first counting is 0 0 0, then it goes to 0 0 1, it should go to 0 1 0, then 0 1 1, 1 0 0, 1 0 1, 1 1 0, and then 1 1 1. So it should count like this way. So it is a up counting, and we need to design the up counter using JK flip flop. Okay, so since it is a synchronous counter, so whatever flip flops we are using, that will be governing by the same synchronized clock. They are synchronized with the same clock. So here let us understand how to write the truth table and how to design it. So we will write the truth table for the synchronous 3-bit up counter. Before going to that, we need to understand and decide how many flip flops we are going to use. So the first step is we need to understand how to calculate the number of flip flops. So here number of flip flops, that must be n. The number of flip flops that should be less than equal to 2 raised to the power n. So here n is 3-bit. Okay. So n should be equal to 8. Okay. So here 8 states are there and 3 bits. 3 bits we are taking. So we need to take 3 flip flops. Okay. These two conditions will go together. We need to check the, let's say we need to design a counter use counting 0 0 0 0, 0 0 0 0 1, 0 0 1 0 like this. So it is having 3 state only, but we are having 4-bit counter. So we will, in this case we will take 4 flip flops. Okay. In this case we will use 4 flip flop because this criteria is satisfied, but number of bits you need to check also. Okay. So that is the key point for deciding how many flip flops we are going to take for designing any synchronous counter. Now next part, writing the truth table. So keeping this JK flip flop excitation table in mind, we will write the truth table. So for writing the truth table, we will write present state, next state. Okay, and 3 flip-flops we are taking, so we will write J3 K3, J2 K2, J1. Okay, so present state is 0 0 0. Next state is 0 0 1, 0 0 1 2 0 1 0, 0 1 0 2 0 1 1, 0 1 1 2 1 0 0, 1 0 0 2 1 0 1, 1 0 1 2 1 1 0, and 1 1 0 2 1 1 1, and 1 1 1 2 0 0 0 again. So this was my present state, and this is now my next state. So I will write it as Q3, Q2, Q1 for present state, Q3 dash, Q2 dash, Q1 dash for next state. Okay, I think this part is clear because at the last we are switching from 1 1 1 to 0 0 0. Okay, so all the state have been covered, all the 8 states, 1 2 3 4 5 6 7 8, right? 8 switchings, 8 states. Now see this Q3 and Q3 dash. Q3 is 0 0, check from here, that is for 0 cross. Again Q3 0 0, 0 cross. It is again 0 0, cross. 0 1, 1 cross. 1 1, check from here, cross 0. 1 1, cross 0. 1 1, 0 1 0, 1 0, cross 1. So we have written for J3 K3. Okay. Similarly, we will check Q2 and Q2 dash. So for 0 0, 0 cross. For 0 1, see for 0 1, 1. For 1 1, it is cross 0. For again it is 1 1, no, 1 0, so it will be cross 1. Okay, again it is 0 and 0, so for 0 0 it is 0 cross. Again for 0 and 1, it is 1 cross. Again for 1 and 1, it should be cross 0. Again for 1 and 0, it should be cross 1. So we will complete the table in this way. Similarly, we will check for, this Q1 and Q1 dash. Okay. So for 0 1, it is 1 cross. So for 1 0, it should be cross 1. For 1 0 1, it should be 1 cross. Okay. And then for for this one, check this 1 0 1 0, for it is cross 1. For 0 1, it is 1 cross. For 1 0, it is cross 1 again, and for 0 1, it is 1 cross, and for 1 0, it is cross 1. So similarly, we can complete the table using the excitation table for the JK flip-flop. So here we have completed the truth table for the JK flip-flop used 3-bit synchronous up counter. Now my truth table is ready. What next step we must perform? So here we will find out J3, K3, J2, K2, J1 and K1 using Q3, Q2, Q1 as input variables. Input variables Q3, Q2, Q1. The outputs are J3, K3, J2, K2, J1, K1. So we need to make 6 K maps in this case. Okay. So let us start with J3, right? Before going to the J3 truth table, we will write the sequences 0, 1, 2, 3, 4, 5, 6, 7. All are okay, all right. So we can directly fill the K map, and we will just draw one K map for example. So what I am saying is, just take Q3, Q2, Q1, 0, 1, 2, 3, 4, 5, 6, 7. So see, 3 at 3, J3 is 1. And for 4, 5, 6, 7. It is cross. So we have this combination, and this combination is only for Q2, Q1. So we have J3 is equal to Q2, Q1. Okay, right? So in this way we will make the K map for K3, K2, J2, J1 and K1. So here we get J3 as Q2, Q1, K3 as Q2, Q1, J2 is equal to Q1 and K2 is equal to Q1. Okay, so all the flip-flops are ready now, all the and if we fill for J1 and K1, you must be thinking we have not made for J1 and K1. So let us check it also. So we need to check, just going to this particular. See here, what is happening is, if you see the truth table carefully, okay, all the entries are being filled. Okay, all the crosses, all the one. That means whatever K map you are going to make, that will cover all the input variables, and hence J1 is 1. Is K1 is 1, because all the entries are here. You will simply make an octet. So for octet in 3 variables, it is always 1 if all the cells are occupied by cross or 1. Okay. So here J1, K1 is 1. Okay. Now coming to the designing part. So all the expressions we have already got. So let us design the synchronous counter. So coming to the designing part. So we will write one output, K3 is equal to K3 is equal to Q2, Q1. J2 is equal to K2 is equal to Q1. And J1 is equal to K1 is equal to 1. So we have reached up to this point. So let us make 3 JK flip-flops. Give This is J1, J1, J2, J2, Q1, J3, Q3, Q3, Q2. All are having the negative edge triggered synchronized clocks. Okay, so clock we have given. Now put the connections. G1, put them on one logic. This is done. Now about J2 and K2, these are Q1. So connect. Okay, connect it, and then J3 and K3 is equal to Q2, Q1. So take one Q2 out, Q1 out, and get this Q2. And also Q2, K3. And hence we can design our synchronous counter using JK flip-flop. Thank you.